Imagine a solid piece of metal suspended in a void, suddenly struck by a powerful external electric field. Conductors are packed with free electrons that instantly migrate to the surface to oppose the incoming force. This internal field grows until it perfectly matches the external one. The forces cancel out, leaving a net electrostatic field of exactly 0 inside. But if we replace that metal with an insulator, a dielectric like glass or pure water, we lose that entire mechanism. A dielectric has virtually no free electrons available to move. Yet when an external electric field passes through a dielectric, the field is still significantly weakened inside the material. If a dielectric lacks the free-flowing charges needed to fight back, what hidden mechanism inside? The material is pushing against the external field. To find out, we have to look past the macroscopic surface. Deep inside the dielectric, the internal architecture is made up of billions of tightly bound molecules. These molecules generally fall into one of two structural categories. This animated diagram illustrates the first type, nonpolar molecules, like oxygen or hydrogen. Here, the centers of positive and negative charge perfectly overlap, meaning the molecule has 0 intrinsic dipole moment. The second type, polar molecules, like water, are shown in this diagram. Their positive and negative charge centers are physically separated, giving them a built-in, permanent dipole moment. They function a bit like tiny compass needles. You might expect those permanent dipoles to exert an electric influence, but in their resting state, they are constantly agitated by thermal energy, tumbling randomly and pointing in every possible direction. Whether the material relies on perfectly symmetrical molecules or chaotic tumbling polar ones, the result is the same. Left undisturbed, the total net dipole moment of the entire dielectric mass is 0. That state of rest ends the moment an external electric field sweeps through the microscopic space. For nonpolar molecules, the field applies a mechanical pull. It grabs the superimposed positive and negative charge centers and physically stretches them in opposite directions. This stretching continues until the external pull is perfectly balanced by the internal forces holding the molecule together, creating what is known as an induced dipole. Polar molecules face a different physical manipulation. The external field acts as a powerful torque, cutting through the thermal chaos and overpowering the random agitation. The field forces these permanently separated charges to rotate, making them stand at attention and align with the incoming force. This animated diagram reveals the resulting state. Whether achieved by stretching or rotating, this dense, collective microscopic alignment is called polarization, denoted by the letter P. How easily these particles fall into line depends on a specific property called the material's electric susceptibility. The higher the susceptibility, the more readily these billions of isolated neutral particles form a unified microscopic army facing the external field. To see how that unified microscopic army affects the whole material, we have to scale back up to a macroscopic view. This animated diagram demonstrates a strange reality inside a polarized dielectric. Deep within the material, the newly aligned dipoles actually cancel each other out. Because a molecule's positive end sits close to its neighbor's negative end, the interior remains electrically neutral. The actual pushback happens strictly at the outermost edges. At the macroscopic surface of the material, the very last layer of molecules has nowhere to pass the charge, leaving their extreme ends completely exposed. We call these exposed, unbalanced extremes induced surface charge densities, or bound charges. The dielectric achieves something highly counterintuitive. Without moving a single free electron across its bulk interior, it transforms its extreme outer edges into highly charged boundaries. Those exposed bound charges act essentially like a microscopic battery embedded directly into the extreme left and right faces of the material. This diagram shows their defense. The surface charge generates an internal electric field opposing the original external force. Unlike the perfect cancellation in a conductor, this rigid induced field only subtracts from the external field, weakening it significantly, but never reducing it to absolute 0. Dielectrics mount their defense without the brute force flow of free electrons. Instead, they rely entirely on the microscopic billion-fold stretching and reorienting of their very atomic architecture to blunt an incoming electric force.